Good morning. How's everyone? How you feeling? This is our last class. And next week will be the final test. You did very well on the last test, so I was happy about that. And I'm sure you were happy about that as a class. You did very well. So giving you more time obviously helps. So for the final test, remind me what we agreed. We agreed that it would be from, did we say 12 to 6 again? So the final exam will be on everything. Yes, you guys like that, hey? Okay. So again, it will be multiple choice, and the format will be, because I only gave you 10 questions or 15, that was like less than 10 questions last time. So you're gonna have more questions, and it's going to be a little bit on everything. And you should be observing the, let's see, I'm going to go into Moodle here. These are all Moodle. Okay, it's going to ask me to log in again. So in Moodle, what you have under the section Final Exam Review are the review problems, practice problems, and then I have here the final exam distribution, and that's what you need to focus on. So 40% is on inference, and then there's a little bit of the rest. Notice I've omitted some topics, and I have here that I would have short answer problems where you choose, and then I have a question from Unit 4. So I think I'm going to stick with this format so that it's mostly, well, it's 24 multiple choice, 16 multiple choice questions. And then there are short answer problems, and you get to choose 5 out of 7. You have to write them out and send them to me. And then there's going to be an exercise from the Unit 4 pages 42 to 48 where I explain the rules of means and variances, and I want you to leave this course having that knowledge, okay? Because that's really important. We don't just operate with one random variable and all the results. We think about combining variables into joint distribution functions, and I taught you a simple way to find the mean and standard deviation of the new function or the new variable. So that's going to be the test. We'll stick with this format. It gives me something to mark, but it's okay for the final test. I will do that. Okay, so you have to write your answers up and email them to me, but part of the test will be. So it'll be part 1 will be multiple choice, and then part 2 will be written. And you can have an idea using the mock exam of what it's going to look like. So this is the exam. You can sit and try this and see if you can complete it in 3 hours, which is really the allotted time. You're going to have more time, but if you can, you should be able to finish this in 3 hours. So you see that's section 2, and then, well, the second section, and then the last part, part C, is to solve a problem using the rules of means and variances. So you should practice that. The answer is hidden. I need to open that up and open that for you. So the solutions are there, but don't watch them right away. Try the exam on your own first and then have a look at the answers, okay? Questions? Remember to refresh your screen if things appear blurry. It looks very blurry. Let's see if I open it up. Looks blurry on my end. Right, Nicole, the multiple choice part will be in Moodle, and also I'll send you I'll have the second 2 parts in Moodle as well. I'll say part A, B, and C, and you'll have to do all parts, okay? Morning, Alec. Okay, so you have to complete all parts. So yeah, we'll just stick with the usual test format. Yeah, it looks very blurry when it's small. Any questions? So Alec, we just talked about the final exam. You should check out the exam distribution, what it's going to look like, and the format. There'll be a multiple choice section, a short answer option, and short answer required portion. So there'll be A, B, and C, and I'll have them all in Moodle for you to answer. And as we said, the test will be, the test will be from 12 to 6 on Saturday, May 15. And we will be done. In the meantime, please let me know if you have any questions. What I want to spend today doing is the last section. I never ended up giving you a replacement video for the t-distribution, so I want to start there and then get into solving inference problems for the mean with sigma known and then with sigma unknown, and then we're going to talk about what's known as paired tests, paired t-tests. Okay, so that's what we're going to do today. We're going to talk about, looking here, so we're going to cover this, and then paired t-test. That's very bad writing. Let me try that again. I gotta move my keyboard. Okay, so that's what we're going to cover today. So we're going to begin with it's called paired t-test or matched pairs test. Oh, I said 9 a.m. Am I generous or what? So 9 hours? Right. So you have that time, set enough time aside to do that. All right, so let's see. Let's look at the t distribution. Do you have any other questions for me before I start? So this is the t-table. And it corresponds to this distribution. This is the t distribution. Now, the t distribution was developed as an improvement upon the z distribution for inference where we don't know the population standard deviation. So this is inference on the mean. So this is like you don't know the population mean, but somehow you know the population standard deviation. If that's true, you can use these results. This is for the confidence interval, this is for sample size estimation, and this is for hypothesis testing. But how realistic is that to know the mean but not the standard deviation? I mean, to not know the mean but to know the standard deviation. So this just helps you build the theory equivalent to what's done here with the proportion. But in reality, if you don't know the mean, you probably don't know the standard deviation. So it's more popular, more common to do this. And that's why you see most of the problems in the homework are using number 6, okay? So if you don't know one parameter, you probably don't know the other. So what happens is we use the same pattern for calculating the confidence interval, right? So this is the point estimate plus or minus the critical value times the standard error. If you don't know sigma, the best guess at sigma is S. But that forces you to compensate for the distribution not being appropriate. Instead, we're going to use the t distribution. The t distribution is different from the standard normal distribution, not in its shape, particularly like that it's symmetric around 0, but the t distribution has wider tails, okay? T distribution, wider tails. And what does wider tails mean? It allows for more outliers. There's more values that are considered different or far away, separate from the rest of the distribution. And what happens here is that we have this table that actually has many t distributions because the t distribution depends on the sample size. And what you see here is one t distribution. So I would say this is like a t . sorry. It's going to be a little bit more flat for T1. And then T2, let's just do something more here. T10. T10 is a little more peaked. I'm exaggerating. A little more peaked. I don't know. Probably not good at this, but it's a little more peaked and more narrow here in the tails. So this is like T10. And then it goes and goes like that, narrowing the higher the sample size until ultimately, after a point, the t distribution looks like the z distribution. So this is supposed to be my z. After some point, let's say T100. T100 looks more like z, and T1000 looks like z. So my drawings are supposed to be different, but okay, let me try this one again. Just a little more flat. And this one's even more flat. You see what I'm trying to get at? Okay, so wider tails, and then they start to narrow as you get a higher sample size, and then it starts to look pretty much like the z. So on the very bottom, after 1,000 observations in the sample, we just put the z standard normal right here. So let's look through the row. Let's look through the row together. I'm going to even this out. Hold on 1 minute, okay? Just hold on a minute. Sorry. All right, I'm back. Questions? Yes, Alec, I know, I need a new T-table video. Yeah, I could. I thought about the same thing, but now I interrupted it by having to leave. My nose is running and I have sniffles, so I just went to make some tea. I'm sure I'm fine, so don't worry. It's just going to be a long day because I have to give videos in the afternoon as well, or make videos. All right, so where were we? All right, so that's what's happening. So each row, let's look at each row. So my tip to you is when you use the T distribution, always draw a picture and remind yourself that you're working in the T by putting the degrees of freedom down as a subscript, okay? My picture is crooked. All right, so what do these mean? Well, you have had practice with the Z table. And if I reference that, it might be confusing because everything is flipped here. I mean, well, the thing is, the probabilities in the Z table are inside the table. And on the margin, you find the Z score. But here, it's flipped. The probabilities are actually up here. And the T scores are in here. The probabilities above, also the other difference between this and the Z table is that the probabilities are the upper right tail probabilities. They're not the percentile, like in the standard normal table. In the standard normal table, the probabilities that are inside are under the curve on the inside on the left side. In the T table, the probabilities are the upper tail, and it says it here, and they are on the top, not inside the table. So you got to remember that. So maybe like remember this is up and this is up here. The other option, if you don't want to use this, you have the option to use Excel. So I'll show you how to do that too. But you should learn both, okay? You should be competent in both, reading tables and using Excel. So what we have here, let's take T10 just because it's more realistic. Let's look at T10. Okay, so let's see. What we have here are notice these numbers are increasing this way and the probabilities are getting smaller. So imagine that we're moving along the T distribution this way, so the probabilities, the area on the right is getting increasingly small. That's what's happening. So if I was to plot these on the graph that I made, %, starts at 0.7. So as I mentioned, so let's say this was 25%. So this would be 0.7 and this would be 25%. And then let's get another one. Let's do 1.813. 1.813. 1.813 would be here and corresponds to 5%. So 1.813, and this should be 5%. Thank you. I already did it. Okay. Thank you. Okay. Questions? So these values give you these probabilities. Now, what is this? I said that this has to do with sample size, but this is not sample size, right? This is degrees of freedom. So the sample size, for sample size, I think I might have missed that part. So we write, if n equals 11, that's the sample size, then degrees of freedom is n minus 1, and that's what I use here. So it is related to sample size, but it's one less. It's one less. Any questions? Let's see. So at 1.813 standard deviations from the mean, where the mean is 0. So in the same way, these represent standard deviations from the mean. Okay? So at 1.813, you have 5% of the observations above it. Let's go and see at a higher sample size, what do we find? Let's try, well, we can just see here, right? So these get smaller and smaller and smaller. So what happens is, I'll just do 20. Let's do T20. It should be a little bit higher. Should be symmetric and all. I'm just not good at drawing on glass. Oh my. I have to steady my hand. Okay. So what's going to happen here, say this is T20. So what happened to 5%? So now it's 1 point. So this narrows and it moves me even further to catch 5%. So I get even closer to the mean. You see, so this becomes like that. 1.725 to catch 5%. Okay, so this is supposed to be, I gotta make it even narrower. See, this is narrower, so to catch 5%, I have to move more in. Okay, so that's what's happening, and that's what's happening to the curve. this is getting tighter, and to get 5% in the tail, you've got to go further in. So, yeah. So that's how you read this table. And I have some exercises to practice using the table, because all I've shown you are values on the right side, but there are also values on the left side which are negative. So how do we deal with that? So let's do a couple of exercises and then apply the table. So for now, what you've been doing, I've asked you to use this table because it nicely summarizes the critical values for popular confidence interval levels. Okay, so just like you could pull out the Z critical values, you could also get the T critical values. So these can also be seen as critical values for confidence intervals. So if you want the 95%, for Z star it's 1.96, but just like I described, it's going to have to be further and further out, the smaller the sample size. So they're higher values. So let's see, let's go to the exercises on the T distribution, and then I will work with sigma known and then unknown. So here are some exercises on page 37 where I apply the T distribution. So this is really what we're talking about, the upper tail probability. For n equals 20 or degrees of freedom 19. So we have to go to the 19th row and see what's happening. So let me just draw this. So this is T. So always draw T, and it's 19 degrees of freedom because n was 20. And we know 0 is in the middle. So 1.5 could be about here. So we're not so familiar with how to draw the T, but 0 is in the middle. I'll work with that. A little bit different than what you know about the Z. So I want to find the upper tail probability of 1.5 on the 19th row. So let's see. Let's go do that. So on the 19th row, we have these values, and 1.5 is not there, but it is between these two. It is between these two. So how do you use that information? 1.328, so let's take that with us. Actually, let's first see what it corresponds to. So let's go up. I'm going to highlight those values. $1.5 is between those two, which corresponds to between 5 and 10%. That's what that means. That's what that means. So let's plot it so we can see it. Oh, I'm on the wrong one. I said 19, right? Let me fix that. It's just a little bit higher. 19. Very similar numbers. So in case I forget, I will take them with me. And put them here. So these values fall around 1.5. And this one corresponds to 10% on the right, and this one corresponds to 5% on the right. So the best, using the table, the best we can do is say that the answer to this question, to the right of the t distribution, and I'm going to put 19 in here. Let me do that again. To the right of the T19 distribution at 1.5 is equal to between 5 and 10%. We don't have an exact value. That's the best we can do. So it's did I grab the wrong one? I used 19 degrees of freedom, right? Let's go back and see. Yeah. So this is the importance of drawing it. It puts everything together. It really does a nice job of putting everything together. Okay, so then let's get the exact answer in Excel. Let's say we want the exact answer. Okay, so we know it's between 5 and 10%, but let's find it in Excel. I'm just going to go back to my page. Okay, so let's see. So we're going to type 1.5 on the t distribution, 19 degrees of freedom, right? So equals t distribution. You have some options. I'm going to use t distribution and then 1.5. And so this is going to give me the left side. The Excel will give you the left side. If I say yes, 1, then it's going to give me the left side. So what I have to do is minus that result. So that is between 5 and 10%, isn't it? Because this is cumulative, this is the left side, or this is the percentile. So you need to know what you're getting. So that would be the exact answer, 7.5%. Okay. Now, before I was teaching fully by distance, I expect students to use the tables, but now, I allow you to use everything at your disposal. So you have Excel, and you can use Excel, and some calculators will make these calculations as well. All right, next one. What if we want to go left? Actually, we already have that answer because I did it in Excel, but how would we go left? What would change? We draw a picture. And what I'm going to put 0 at the bottom, and always write the t-distribution name inside, so I don't lose sight of what I'm doing, because we have a few different distributions to use and it can be confusing, right? This way it reminds you to go to that row. So let's see, we're going to plot, we want 1.5 again, but we want to go left, so we want to go this way. Well, let's first use the table. On the table, I'm gonna steal these? No. Let me take it. No. Okay, so I'll just write them again. Using the table, I know that right here is 1.328, and over here is 1.729, and that marks 5% this way and 10% this way. But I'm in between, and I'm going the other way. So how do I do the flip side? Well, let's rewrite these going the other way. So let's write that. If it's 5% to the right, then it's 95% to the left. And if it's 10% to the right, then it's 90% to the left. So the answer is just a matter of seeing that it's between I'll do them in numerical order, 90% and 95%. And then in Excel, what did we get? Let's go back and see. We got 92.5, so we'll go with that. 92.5, which is reinforces what we got. Okay, so that's how we use the table or Excel. What Excel has programmed in it is all this information. It has the function. It has the ability to do to calculate the area under the curve, which is integration. So it can figure out any of these values here continuously because it has the functional form programmed in it and the ability to do integration in that functional form of the derivative. So anyway, or and not the derivative, but the integral, if you know what I'm talking about. But you don't have to worry about that. You see how easy we've made it for you? But I don't want you to lose sight of where this all comes from. This is, okay, so let's see number 3, unless you have any questions. Okay, Excel. Let me show you the formula. So that was to get it on the left side because it says cumulative. If I don't say cumulative, what do I get if I say 0? Not cumulative. Does it give me the right side? No, it just gives me something that I don't even know what that is. I went through this before. I'm a little bit confused what it's giving me, but I want the cumulative because that's the left side. And then I get the right side by doing 1 minus. Okay, so let's see if I do t. There's a bunch of options. There's different kinds of t distributions, but you want the t distribution. I wonder if this is for matched. No. It's not that one. Let me try this t distribution. So that's to get the probabilities. And then there's the formula for what if you want the reverse. So that's what we're going to do next, and we'll look at that. Questions? Okay. Let's go back. Next. Find t so bad in my lines. Let me try. No, let's do, okay. Negative 1.44. Remember, 0's in the middle, and this is T6 because degrees of freedom equals n minus 1 equals 6. So that's T6, and I want negative 1.44. So let's mark it. Negative 1.44, and I want to go this way. So this is, again, area under the curve to the left of this number. Now this number, a negative, is not on the table, so what do? I use symmetry. I use symmetry and I say, well, I can do that, or it's the same if I go this way. And let's see on row 6 how close we get. So let's go to row 6. So you should print these tables and have them in front of you. Okay. Let's see row 6. Let me make this larger and look for it. So I made it easy by putting it in there. Okay, so it's right here. The upper tail is exactly 10%. Let me clean this up a bit. So for the 1.44, okay, Let's go back. And so this is 10% over here. So then, of course, this is 10% by symmetry. So the answer is, now if you just draw it, I'm happy. I'm very happy if you just draw what you're doing. Now let's try it in Excel, because then we don't have to do the flipping. So let's try for t, actually I want to put 6 here. Always put the degrees of freedom. I did it here as well, right? Okay. Let's go to Excel. So let's do equals t distribution, and then here we're going to put negative 1.44. The degrees of freedom is 6, and we want cumulative. So this would actually give us our answer right away, 10%, if you round it to 2 decimals. Okay. All right. Should I let you try a couple by yourself? Okay, we'll just do this one by yourself. So try this and I'll check back with you. The answers are in the notes, but try and get the answer as like solution. Try and solve it. Okay, so how'd you do? You want to watch me? Ready to watch me? I'm going to move this over a bit. Okay, let me erase this space. Make some space, and then so if I mark negative 2.086 and I go this way, that is not on the chart. So I'm going to draw it again. I'm going to try to draw it again and change the direction and sign, right? Direction and sign. I'm going to go direction this way on 2.086, and I will go that way, and I'll have the same result because of symmetry. So the table only gives me the right side. So if I go to, I have to write T20, and degrees of freedom equals n-1 equals 20. Now I'll go to the 20th row and look for this number, 2.086. And now it's a large area, right? It's not the upper tail. I have to do 1 minus to get my answer. So let's go 2.086. 2.086 on the 20th row. Look, see, I made it easy again. Made it easy for you by putting the number in the table, which is fine. Just some practice on using this table, interpreting. So it's right here, 2.086, and it corresponds with 2.5% as the upper tail. So exactly, Gerardo, got it right? Alec got it right? Okay, so that's going to be 2.5% on the right. There's got to be an easier way to get from one to the next, shouldn't there? I have to figure that out. Scrolling takes a while. So this is 2.5% from the table on this side. So that must be then 97.5% on this side, and that's my answer. Since that's the same, then this must be 97.5 here. So you got to draw it and know what you're dealing with, or use Excel. But still, you have to understand what you're dealing with. So the answer here is, I'm going to just circle the right answer. So let's try Excel. We're going to have a degrees of freedom of 20 and 2.086 negative. But we want the area to the right. Remember to put the degrees of freedom there. So this is the area to the left, the 2.5, and then we have to take 1 minus to get our answer. And so the table's pretty good. Okay, so you guys are good at this. So now let's look at, rather than trying to find probabilities, we're going to do the inverse problem. Let's find the critical value, or the t-score. So that's type 2 type question. So instead, I give you the probability and you tell me what t is. Now this is actually much easier than for the z distribution. I'm going to draw here in case I need the space. So for this is for T16, right? Because degrees of freedom is n minus 1 equals 16. And they're telling you that at this value that I want, there's 5% to the right. Not sorry, 0.5%. So I'm going to draw it here. Or I'm going to draw it here. And I want to find T to make 0.005 or 0.5% on the right. So where are the tail probabilities? They're on the top of the chart, so I have to look for this number on the top and then look down. So it's the inverse opposite behavior. Starting with the probability, I can find the t-score. And you're going to see it's very easy. So I just go to the top and I look for that number, and then I go all the way down to, what were we again? 16. I have to go back because I don't remember what it was. So let's see. It was 16, right? So for T16, 5, this is the value for 0.5% or 0.005. So the value is 2.921. I'll erase all of these. It's hard to see. I'll use a different highlighter color. So 2.921. And it looks like that makes sense, doesn't it? Right? Now let's do it in Excel. In Excel, you want to do the inverse calculation for the upper tail. So you have to keep in mind that's what you want. What does Excel give you? Excel equals T inverse, this one. You have to give the probability 0.005 and degrees of freedom, and I guess it's going to give you the left side. Let's see what happens. Or does it give you upper tail? It doesn't even explain it. There must be instructions. Anyway, let's see. 16. What does it give me? So it gives me the left side. Okay, so it always works with the left. And it's the left side, not the probability, but the critical value. So that's the formula. So you need to know what you're getting. If you put that in, it's just giving you the left side, and you need to know how to interpret that. Okay, so then if you want the right side, you have to change the sign. So you have to be very proficient in the symmetry of these distributions. So they gave you this side because it's customary to give the percentile. So interpret the 0.005 as a percentile. Okay, so you need to know what you're getting. Okay, so let's see for this problem. You probably don't need to use Excel for that because the table is pretty easy. And you're reading right off the table, unless they give you a probability that's not on the table. So this will be T9, and this asks to find the T that corresponds to 0.005 on the left for T9. So because the table only gives you the right side, you have to realize what you're getting, T9. If you go to the upper tail and look for that number, you need the negative of it to answer the question. So going to the table for T9, let me erase this. So I'm going to go down here to T9. It's going to be 3.25. So the answer is the left side. So the answer is negative 3.25. Okay? And I have all the answers. I give you all the answers below so you can practice. And I use symbols, but the graphs are fine for me as long as you understand. And the graphs help you understand. Use the graphs. Use the sketches as opposed to writing out everything properly. Okay, that's the T distribution, all right? And now what I want to talk about is solving problems with the T distribution, but first I have to go back and deal with what if sigma is known. So let's deal with that case first. Let's go back. So some of you have probably read through the notes. Some of you feel like you know this stuff. That's great. Review doesn't hurt, right? And those who want me to help them get through the notes, I'm here. So what I want to do is begin with the confidence interval. Page 18. So because it's a continuous distribution, Gerardo, it doesn't matter if it's less than or equal to or less than or greater than or equal to greater than. They mean the same thing because putting an equal doesn't change anything. So I don't know, some textbooks use with the equals and some don't. I'm not sure on that philosophy, but I guess they're trying to be consistent. And anyway, equal doesn't add anything in a continuous distribution. In number 5, let me see if I did something wrong. In number 5, we were looking for the right side. Number 5. No, we just read it right off the table because the way it's written, it says the distribution to the right of t is this small number. To be the right of t and a small number would be up here. So you just read right off the table. Nicole. Okay. All right, I want to start here. This is page 18. Confidence intervals. So what we're going to do here, what we're dealing with is the, don't worry about it. Actually, I'll talk about that after. So what we're dealing with here is making a best estimate of a mean, as opposed to before we talked about the best estimate of a proportion. Now we're going for the best estimate of a mean, and we're going to use the sample mean and the theory that we built about the sample mean. Remember back when we talked about the sampling distribution of the sample mean in SDS. That was the SDS unit. And X bar has a distribution that is approximately normal, or normal depending on what you know about the original distribution, right? So I've summarized those in number 3 of the formula sheet. So that involves the central limit theorem when you don't know that you started, you're drawing from a normal distribution. You use a central limit theorem to gain results about the sample means distribution. So that's what we're going to apply here. Okay, so we're going to say that we have, okay, let's work with this example and you'll see what to do. A simple random sample of a size of 100 is taken of women in Canada in hopes of estimating the true average height, mu. So they don't know it, they want to estimate it, of all women 18 years of age or older. So when we worked with SDS, usually you were given information on mu and sigma. Well, we don't know mu. The sample average is calculated to be 5 feet 4 inches or 64 inches in total. The standard deviation of the actual height of women is known to be 2 inches. Aha, so they gave us this information here that sigma is known to be 2 inches. Now how they know that, I have no idea, but it facilitates making these calculations. So what we have is mu unknown that we want to estimate, but sigma is known. So we want to make a confidence interval. Now we learned about confidence intervals with proportions. The same principles apply. What we want to do is not just use the sample mean from the sample, right? We don't want to use just the one that we got. There's a whole theory about the distribution of sample means, because this is just one, but it comes from a distribution. Now here we don't have any information on the original distribution, but we're told n is equal to 100. So with n equals to 100 and this information here, then what we do know is that X bar is approximately normally, well, let me write it out in the bottom part here. So what we know is given X with a mean of mu is unknown, sigma is known, we don't know the shape, but because n is equal to 100 and that's greater than 25, then we know that the sample means come from a distribution that's approximately normal or regular or predictable with the same mean, even though it's not known, and a standard deviation that's smaller, like this. So because of this, the central limit theorem, we're able to make estimates about what the mu is. Basically, we're going to use this bridge to go back to figuring out what this is. Okay, so the best guess at the mean will be x bar. And then we're going to, because it's normally distributed, we're going to build an interval of 2 or so standard deviations around it. This is the standard deviation we're going to use, and whether we make it 2, 3, or 4, we translate now into a more precise notion called a confidence interval. So in the first case, we want a 95% confidence interval. So what is that? Let me move this. Hold on. So what is a 95% confidence interval? So this is going to sound repetitious because I did this for the proportion, but some of those people who like or appreciate it, this is for you. Okay, so I want 95% in the middle, where this is a standard normal curve or any normal distribution. For 95% in the middle, what would be the cutoffs if this is z or any normal distribution? How many standard deviations away? Z will give me the value of the critical value as the number of standard deviations away. Well, if it's 95 in the middle, then it's 2.5 on either side. So I have to find the place where it's 0.0250. I need to find this, and that will tell me how far away I am. So if we went into the the Z standard deviation table, what am I saying? The Z standard normal table. The standard normal table, we could look inside the table for this number and find the critical value. Or we can go to the T table at the very bottom where it turns into the Z distribution and read the value off. But let me show you both just in case I don't want you to forget how to do this, right? To find the critical value. So let's see, we're going to go look for 0.025 inside the table here. Now it should be on the negative table, it shouldn't be here. So if I look for 0.025 inside the table, this is the standard normal, 0.025 would put me here, you see? Which corresponds to 1.96 negative. So also we would have seen that if we went to the T table at the bottom and looked for 95%, and then here we find that it's 1.96. So there's 2 ways to find the answer. Okay, you can use the T table or the Z table. So that's how many standard deviations away I need to be to get 95% in the middle, 1.96. So this is counter what we learned before. It's kind of, we learned before that 2 standard deviations, right? It was 2 standard deviations, but that was just a rounded value. That was just rounded off. Oops, sorry, I'm not in the right place. That was just a rounded value. It's not exactly 2. It's 1.96. 1.96, which if you rounded it to a whole number, or to to a whole number, it would be 2. But this idea of confidence intervals is more precise, and I want exactly what should it be, how many standard deviations I'm away. So what we're going to do then for a confidence interval is build using the formula that you have already, but I want you to understand it, and that's why I'm reviewing this. you want to build around the best estimate x bar 2 standard deviations away, but more precisely 1.96 standard deviations away, and standard deviations have the symbol sigma over root n for x bar. Right? That's what I'm using that result. So I'm going to put these numbers in now. So this is going to be 64 plus or minus 1.96, and oh, I need sigma over root n, so I can just write it here, 2 over square root of n, 10. Well, I'll write it all out first. Okay, so you can make a confidence interval, and I go through the steps in the notes to just adding this together. Now we call this together part here, this part together, as a margin of error. Let's figure out what that is. .392. So this is 0.392, and this is called the margin of error. And this is plus or minus 64. So you can write it like that. You can make the actual interval. So you're going to take 64 and minus 0.392, so it's going to make an interval of 63.608. You can let me know if I made any mistakes, and 64.392. Very precise, isn't it? And what we say about this is that this is a 95% confidence interval for the true mean. So this confidence interval that we made, just like the mean that we got, comes from a distribution of confidence intervals. Like, there's so many different confidence intervals we could have gotten, but we got this one. And what a confidence interval says is that 95% of the confidence intervals you could have calculated from all the possible samples will actually have the true mean in it. So the idea is, let's say, actually I need to join these together. And I lost something. So I describe here let's say the true mean, let's say on a scale, the true mean is like here. and this is a 95% confidence interval, or 95. This is an interval around the true mean. Then from different samples, let me make it smaller so that I can fit it. Let's say that was the interval around the true mean. But then what we're going to do is collect samples and make a confidence interval around x bar. And that one might be on a number line, maybe it's here. And then we manage here to just catch the true mean inside, you see? Now we could have had a different confidence interval if we had a different mean. Now it's going to have the same width or length, but maybe it's centered at a different mean, and it also catches the true mean, you see. But there could be a confidence interval, and 5% of all possible confidence intervals by the theory will not capture the true mean. So this one will miss it. You see, it's not even close. So that's 5% of confidence intervals will not contain the true mean. But out of the 3 that I did, these 2 did. Questions? All right, so let's, so what I did is I solved this for you in the notes, but what I really want to talk about is understanding this stuff. Okay, what happened here? Let me do that back again. All right, everything is together. Okay. So we have here the confidence interval that's 95% for the true mean of women's heights, and that's part A. So that's part A. What about part B? What does it mean, accurate 19 times out of 20? So being accurate 19 times out of 20 is the same as 95 out of 100, isn't it? In other words, this is another way to say so this holds true for the proportion as well, this interpretation of confidence intervals, okay? So some people say 19 times out of 20, it's easier for some people to understand than saying 95% confident, but they mean the same thing. So your answer will be the same. And then I ask you to calculate this for a 99.7% confidence interval. Okay, so let's see. What will change? What do I have to do different than what I've already done for a 99.7% confidence interval? No comments? What changes for C? So C, you do the same thing as you did before, but now you're going to use Z star. Everything's the same, just Z star for 99.7%. And where are we going to get that from? Let's see if we have it on our table. The easiest way is to go to the T table at the bottom and see if it's there. 99 point, it's not there. So what do we do? Well, if it's not there, then we have to use the standard normal distribution. And what we have to do is look for where is their 99.7%? So it should be near 3, right? But if it's 99.7 in the middle, then it's 0.15% on either side. Or in other words, 0.0015. So we look for this number inside on the left side, because that's what the table gives us, and look for the value. So 0.0015 is here. Or you could use Excel. That's the other way to do this. So negative 2.965 looks like the answer, because, sorry, it's between these two. So the answer would be negative 2.965. So it's pretty much 3. It's very close to 3 if you round it. So you just found this here. Okay, so let's go back and fill that in. Okay, let's see. 2.965. And that's what I did here. Okay, so I have the answers here. So that's not on the table. You need to use the standard normal to find that. Okay, so when you finish, you get this interval. Now this interval is wider, right? Because it's 99.7% confident. It's much higher likelihood of having the true mean. To do that, to achieve that, it needs to be wider. So this is a wider interval than the one that was 95%. Okay, I'm just gonna take a little break. I'll be right back. You guys can work on the last one. The last one, this one here, if you haven't already. That's an easy one because you get the value for this Z star. Okay, I'm back. So how'd you do? So for 99% confidence, the critical value from the table, the t-table, is 2.576. So that's the one you're going to use. Okay, so that's the easiest. 2.576. And that's what I do here in D. 2.576, it's a little bit smaller than the last one, it's a little bit bigger than the first one, and that's the confidence interval. We refer to this as the margin of error. Any questions about confidence interval estimation? Now, what do we do if we don't know sigma? What do we do if we don't know sigma? If we don't know sigma, we have to use the best guess of sigma that we have, and that is S, the sample standard deviation. But to compensate for using an estimate instead of an estimate, we have to use the t-distribution instead. And it depends on the sample size using degrees of freedom. So what I'm going to do is do this for now, the case of not knowing sigma. So I'm going to seem like I'm jumping, but it's because I want to make sure I cover everything efficiently. So now that you have that in your mind, let's take away sigma. And let's make a confidence interval. Here's my example on page 41. So let X denote the weight of a certain breed of dog measured at age of 3 years. It is natural to assume that X follows a normal distribution. Okay, so you get this information. This is important. It makes everything easier. You get it from a simple random sample of 5 such dogs. So you get a simple random sample of 5 such dogs from this distribution, right? And here they are. And that's it. We're going to assume that the true mean mu and the population standard deviation are unknown. And we're going to use the results that are described in the notes, that if this is the case, and you start with a normal distribution, taking a sample from them, even if it's small, is approximately, that sample mean of this will be approximately normally distributed. Okay, so what we have to do is use our calculator now to get these, the values of the sample mean and sample standard deviation. These are known as the moments, right? First is the sample mean, and then the sample standard deviation of the 5 weights. So putting those into the calculator, putting those into our calculator. We're going to check out data. So there's something in there and I need to clear that. So second, clear work, and I start to enter my values. 10.9, enter down. Now I'm just entering for one variable, not for two. So it's just frequency 1 there. Or we're just not entering y, don't worry about it. So the second one is 12.6, enter. And skip over y. And then 10.2, enter. 15.2, enter. And 11.1, enter. And now ask for the statistics. Actually, let's check first that we entered them properly. So, oops, no. What I want are, what happened? Try that again. 10.9, enter, down. Oh, what happened? So 10.9, 12.6, everything disappeared. I must have erased it. 10.2, 15.2, and 11.1. And then ask for stat and go down. I still want to see what I have in my data. It's all there, right? It's all here, 12.6. Okay. So I ask for second stat and I get my results. My mean is 12 and the standard deviation is 1.991. Okay. So go back. So the mean is 12. And S, oh, I didn't even write it. And S is 1.991. And I'm keeping 3 decimal places because these ones had 1. So I keep 2 more than I started. So that's why I keep 1.9191. Now I don't have any information on sigma. That's why I had to do this. So this is more practical. This is what people end up doing. They use a sample, estimate the true standard deviation, and then use it to make predictions or to make a inference of what the true population proportion is. So now calculate the standard error of the sample mean. Well, we know that X has a mean, X bar has a mean of the true proportion. I mean, let's see. Let's go back here. I explain it all in here. Okay. So this is the symbol. This is what I'm using. So a T distribution is a standardized X bar provided that the underlying population is normally distributed or close to normal, and even if you start with a skewed distribution, as long as the sample size is greater than 30, you're okay to say that this is the standardized value is approximately, or it's normal, t is a t distribution with n-1 degrees of freedom. So don't let the symbols intimidate you. Basically, I'm going to do the same thing, but where the standard error is, rather than sigma over root n, because we don't have it, we use s over root of n as the standard error. So s over root of n is 1.991 over square root of 5. So this is the standard error because we're using an estimate inside of the estimator. So this represents the standard deviation of x bar. So I have the answers here. 0.89, okay. So this is 0.89. Now how many degrees of freedom does this distribution of x have? It has n-1 or 4 degrees of freedom. And I ask you to make confidence intervals. So now what you have to do is use the t distribution to find the critical values. So before we begin, because we're going to make confidence intervals, let me write down the formula that we're going to use. So we're going to use x bar plus or minus now t star and s instead of sigma over root n. So this is the interval we're going to make because it's going to be 1, 2, 3 standard deviations from the mean, or t star standard errors from the mean. That's what we're going to call them. So we need the different t stars. So let's get those first, and then I'll leave it for you to calculate. So for t star of 90% confidence is what? T star for 95% is what? So all we have to do is go to the table and look from the bottom up to remember we're working with T4. So you have to go to the 4th row. So if we go to the table and the 4th row, we'll get our values. I'm going to copy them. I'm going to take them with me. So we want, oh, sorry, we're going to start at the bottom, I said, right? So it was, well, let's take them, let's clean this up a bit. Let's clean this. And what I want to do is get for 95, let's get all of these here. So we have from 90, 95. Yeah, so let's take all of these, but in the 4th, from the 4th row. So that begins, I have to go up, right? So 90% is 5% in the upper tail because it's 90 in the middle and then 5% on both sides. So what I need are these values here, and I'll take these ones. Take those ones with me. Oh, you know what? I'll take the whole thing. Let me do that again. I'll take this whole thing with me. That wasn't a good idea. Okay, do that again. Clean this first and take it with me. What is happening? Okay, let me go back to my problem. Okay, so these are the values from the table, right? And these are the upper tails. So this corresponds to, because this is the upper tail, so this is 90% confidence. And this one would be, if it's 2.5 on either side, this is 95% confidence. And this one is 96% confidence, and this one is 98% confidence, and this one is 99% confident. So which one do we need? So you see what I did? Because I can see this is 5% in the upper tail, so then that's really 10% in the tail, so that means 90% between. This is 2.5% in the upper tail, so that's 5% total in the tail, so that's 95% in between. This is 2% in the upper tail, so that's 4% in the tail, so that's 96 between, and so on. So for 90%, this was 1, 2, 3, 4 degrees of freedom. So I ignore, I just want to use the fourth one, just these. And the one that I want for 90 is this one here. So 2.132. And for 95, it's 2.776. And then for, what else do they want? 99. And for 99, it's going to be this one here. So that's all I need to answer this question. Then using the formula with this already computed, and we know this already, this is 12, this one is 0.89, you can just re-estimate the confidence level, and it's in the notes provided already. So you should practice making those calculations. You can write the interval. You can leave it like this, or sometimes you'll be asked to actually create the entire interval. So here are the results. These should look familiar from the table. So So 12 all the way down and 0.89 all the way down. All I'm changing is the critical value. And then either you can leave your answer as a interval written like this, or actually compute it. Go add and subtract the margin of error and make an interval. Okay, and I just closed that. I didn't want to do that. I want to do the hypothesis test. Let's do the hypothesis test together. So if sigma is known, you would use it and use the z table. If sigma is unknown, you have to use the t table. Before we do that though, we need to solve this other problem of finding sample size estimation. Okay, so all I've done so far on our formula sheet is I've done these two together. So I've covered both of these. Okay. Now I'm going to talk about this. This is going to be easy because I'm only going to solve it for here, not for here. And I'll explain why. Then I'm going to do a hypothesis test, and I'm going to have to quickly do a matched t-test and tell you about that. So what about sample size estimation? Remember where this formula comes from. This formula is the margin of error. So if I preset the margin of error as a number m, then it would have to equal this, right? And in that case, if I wanted to know the sample size, algebraically, so let's say I set the margin of error. I say I don't want it to be wider than having a margin of error of 1% or 0.01. So I set that. And I also set that I know the confidence level that I want. Then nature just gives me the sigma. God tells me what it is. And so let's say I know it. Then I can solve for n. So isolating for n means that m would come down here and root of n would go here. So n must be the square of this. Okay, so that's where that formula comes from. It comes from setting the margin of error, and then it becomes a denominator value here. All right, so this is important because, well, I want to estimate a parameter I don't know, the sample, the true mean. So I want to estimate a parameter I don't know, the true mean. That is what I want to know. I'm going to use the sample mean as a best guess, and that one sample mean comes from a distribution of means. So that means the one that I got is not necessarily mu, but I can use it because of the theory to make an interval of values that probably contain the mean. Well, what sample size should I use? That's a question even before doing this, right? So what sample size do I use? And this is the formula for calculating it, okay? You need to know sigma. If you don't know sigma, look, you can't even do it. Now there is a way to do it, but not as an isolated algebraic result. It's not going to be that straightforward. You could do it. Anyway, we'll talk about it after. Let's solve this first, okay? So let's try a problem with this. So I'm going to go back to the discussion over here. Sample size estimation on page 20. So we've already solved for our formula. This is similar. When we did this for proportion, we did the same thing, but we had obviously a different result because we were dealing with proportion. What we want to solve for is for this example, for women's heights at 64 inches on average in a sample of 100 with a standard deviation of 2 known, population standard deviation, what should the sample size be to obtain a margin of error of 1 for a 99.7% confidence interval? So what you have to do is use a formula. I mean, you could plug everything into here and solve this just the same, but this just it leaves. Anyway, this is the formula for it. If you use that, you should get the right answer. So I've done it here for each of the cases. This is for, let me get the questions. I didn't want to do that. Oh dear. And I lost it. What just happened? Okay, so for the first one, this is for 99.7% confidence. That would be the Z star. These numbers are the same all the way down, you see, because those are set already. I'm just varying the level of confidence here. Sorry, no, I changed M here. So this one is level of confidence 99.7, and as well, this one is 99.7. But what I change from here, I use sigma of 2 because that can't change. I don't get to choose that. That's a given. But I can choose the margin of error I want. So this one I'm going to let it be tighter with 1, but this one's a little bit bigger with 2. So how does that affect things? At 99.7% confidence, look at the very difference in the sample size estimation. If I don't want to be so precise, I'd only have to estimate about 9 women. We're going to do that next, Alec, because we need to do this first, and then I'll do the hypothesis test. I'll go back to that one. So that's the effect, okay? So if you don't want so much precision, the margin is larger. In other words, you don't need so many women. Remember, when we round, we have to round all the way up. So 8.79 goes up to 9. And 35.16 goes all the way to 36. It doesn't round down. It always goes up. And that's to maintain the margin of error of 1. If we went down, the margin of error might be too big. Okay, so we need to round up. What about the next two? This is 99.7% confidence interval with a margin of, no, sorry, the first and the last. So different confidence levels, but the same precision in the margin of error. So these have the same 1 for M, but I've changed the confidence level. So more confidence, it's going to be a wider interval than here. So having more confidence with the same margin, I also have to sample more people, okay? So the N is going to be higher. You can just see it right in the formula. The N is going to be higher. The higher the level of confidence, that will make Z star higher. Or the lower the margin, so the more precision. More precision and greater confidence will increase the sample size. So you guys can practice those calculations and using that formula and reading through these notes about it. What I want to talk about now is, what if we don't know sigma? What happens to this formula? So in other words, why is there nothing here? Well, let's say there was something there. Let's say it was, what's wrong with this? Why can't we just do that? Just like I put an S in place of sigma and use T, why can't I just put S in sigma? No comment? Why can I not do this? Well, I cannot do this because S is equal to notice S has an N inside of it. So by writing this, I haven't really isolated for N. So you're not really solving for N. You have N inside. So what you could do is use some sort of iteration. I mean, you could pick values. You could put this in Excel as a formula, you know, with this inside, and then just keep on picking N's. And seeing how it affects this N, but it's just, anyway, it's not a pure analytical solution. It would be maybe computational or iterative. So we don't teach you that right now, okay? So that's why you're not really completely solving for N. It's a lie if I put it in there and covered up the fact that there's an N inside of S. So that's why it's not there. So you only have to do this for when sigma is known. So now let's get to hypothesis testing. So these are, notice, these are the standardized values. In the case of knowing sigma, this standardizes to make Z. And when you don't know sigma, this standardizes to make T. Now you have to keep that straight. You need to remember that. If sigma is given, use the results in number 5. Okay? That seems obvious, but sometimes people are given sigma and S as well. Don't get deceived. you still want to use the results in number 5, okay? Because sigma is better than S. It's the true proportion. This is just the second best thing, or the next best thing is to use T and S in place of sigma. So let's solve the problem for the dogs, and then you guys will have to practice when sigma is known and sigma not known. You can do the homework exercises. It's full of examples. So mostly in the homework exercises, you have case of sigma not known. So that's why I'm teaching it this way. So you got to keep, you need to remind yourself where you're at and which distribution you're using. So I have many examples in the notes, very many examples, but you have to work through them. So let's see the dog. Okay, here's the dog. So again, this is for averages, all right? This is for averages. So we want to test the hypothesis that the dogs weigh 14 kilograms against the alternative that they weigh less than. So that's pretty straightforward. What you have to remember, we're going to work through the steps just like we do before. It's my niece again. Sorry. I have to call her. She's going to keep calling me. Hold on a moment. Sorry about that. I have to turn off so many devices for the sound. Let's see if that helps. Okay. All right, so we start with the hypothesis. And now that we're working with the mean, we use mu. But the same approach, we're going to use an equal sign, and whatever number I put in the null, I also put it in the alternative. So this is pretty straightforward. It's nothing really hidden here. We want to test the hypothesis that dogs weigh 14 against the alternative that they weigh less. So this gives it away to me. This is 14 and then the same number here. And it tells me explicitly in the alternative I want to put less. All right, so that's the first step. Now the next step is assume. Assume, so we can't do anything because we don't know much. So we're just going to assume H naught is true. Now that means that we were given information that X is approximately normal, right? The weight of dogs. And we have a small sample size, but that's going to be fine to make the assumption or to make the leap to say that standardizing the sample results, so I'm going to do this together. I'm going to assume and assess the evidence at the same time. I'm going to do them together. So I know that this will make a t distribution. This will create a t-stat for me if I do this. If I standardize the result. So I know it's going to be approximately t distributed with this hypothesized mean and this approximate standard deviation, or this estimated standard deviation. So that's what I'm going to do to calculate or assess the evidence. So I put the numbers together. Remember that this was the value I got from the samples, 12. Then I minus 14 because that's what this is. These are the hypothesized value. This is the hypothesized mean here. And then the S, remember, was, well, S over root n, we already calculated as 0.89. So we already made that calculation. And we end up with a value that's negative, telling us that it's lower than the hypothesized value, which kind of fits with what we were suspecting, right? So this is negative 2.25. So this means that this is 2.25 standard deviations below the hypothesized value. Now, is that far? Does that make the result of having a mean of 12 very different or very bizarre? Like, is it very rare that we would see that when we're supposed to see 14 on average? So because we're not so familiar with the t distribution, we want, this is the value of turning this into a p-value, right? Like when we were working with the z, we knew if we were outside in the outliers, we had a better sense. I don't know with a t of 4, is that an outlier or not? Okay, so let's check. Let's make the p-value step. Remembering the p-value is the probability of being or seeing a t-stat in this case, or we'll just say in general, a test statistic as extreme or more extreme given H naught is true. So what you do is you draw a picture, and this is your chance to put T and the number 4 down, right? Because it's 4 degrees of freedom. And you remind yourself of what you're dealing with. So then we mark negative 2.25, and we find the value to the left, of that. And that will give us a p-value, because that's the probability of seeing a t-stat as extreme or more extreme given H naught is true. So the given H naught is true was incorporated here when I standardized using H naught or mu naught. So let's see, negative 2.25, we know how to read the tables we have to convert this into the right side. And go to the fourth row. So on the fourth row, 2.25, where is it? So it's not here, but it's between these two. So let me cut that out. So what did we see here? That for the fourth row, $2.25 is not there, but it's between these two. And these two correspond to between 2.5% and 5%. Again, you can put it in Excel to get the exact number. Now, why did I go in this direction? Because that's what the table has. Although I want this direction, I use the right side to get the answer. And then I put my answer on the right side, on the left side. So this is also between 2.5% and 5%. All right, so it's not 5% because that would have been lower. Sorry. It's not 5% because that would have been like closer to 0 over here, right? That would have been 5%. And it wouldn't be 2.5% because that would be closer in the tail, smaller. That's 2.776 away. So it's in between. So finally, we can conclude that's all my p-value would be called between, this is the p-value, and that's the best I can do. Or I can go to Excel and get it. So the concluding step then is the same. Remember, I check on the left side because this is where I use the alternative. I check on the left side. So you need to remember this statement and test it, entering the value. So my answer is between 2.5% and 5% is smaller than 5%. So it means that the result was strange according to the threshold of 5%. So making it suspicious that the null is true. We have found evidence to suggest the null is not true. So we reject the null. So in this case, the test is significant. We reject the null, the test is significant, there is sufficient evidence my notes are getting messy. There is sufficient evidence to suggest their weights are less than you stick to what's in the hypothesis, less than 14 kilograms. You don't have to say that they're 12 or it's just one result. You don't say that that is exactly what they are, because remember, we're dealing with the distribution of sample means. And based on what we assumed, we have evidence to suggest that their weights are less than 14 kilograms. All right. Any questions? So when you read problems, you have to first determine, is this problem about proportion or is it about the mean? Next, you have to determine if it's about the mean, do you know sigma? Okay, so the things to ask yourself, I don't even want to say step 1, but because I have so many steps already, let's just say first, is it about mu or about proportion? Second, if mu is sigma known? So those are the first questions. Those are the questions you ask yourself, okay? And then you know what to do. The direction is determined by the alternative hypothesis. All right, so work with those. Let me know if you have any questions. Before we go, I need to talk about the t-paired tests, which are just like t-test that we've just done, but it's for two samples that are paired. So I need to talk about that and leave you with that. So I'm going to take the next 15 minutes. Then there's some data in here as well. So what we can do, if you have any questions, I can host office hours in the week, maybe on a Thursday, and solve some problems. But you do have a ton of videos to go through and watch me solve problems. You have a lot of notes. I'm just looking for paired testing. No, not here. Okay, so this is not going to be on the test. So follow along. Here it is. So here I am on page 46. I didn't go so far. So you can also do a t-test You can also use the t-test for 2 samples. Because all we've been working with is 1 sample, right? But if your 2 samples are related, if they're dependent on each other, in other words, they're not independent samples, you can combine them to make a single sample called the differenced sample and analyze it just the same that we've done all along. So here's an example. This is for dependent or they say matched pairs. So this goes back to when we learned about what matched pairs designs were in experiments. And I promised you that you would learn how to analyze results of matched pairs experiment. And and now you have all the tools, so here it is. Okay, this is how you would do it. So this is known as dependent samples or matched pairs. We have here information from an experiment using an old fertilizer, and we have 4 plants that were these are tomato plants, and these are the pounds of tomatoes they produced when the old fertilizer was used. Okay, now these are 4 different plants but matched, so either they're nearby or they have the same exposure. In other words, they're matched on variables that determine productivity of the plant. But the only thing that's different in this controlled experiment is that the new fertilizer is used instead. Now with the new fertilizer, it looks like for this plant that's matched, there looks like a lower yield, but is this statistically different? Is there a significant difference? That's the question. Well, look at this one. This one is higher. And this one is higher. And this one's a little bit lower. So we need to put all this information together, but doing it with 2 sets is not the way to do it. What we do is we difference the data and create a new data set. So we have a new sample. And we basically ignore these. So the way that was calculated is I took the new value minus the old value to generate this new sample. And this is the one I analyze as though it's the t-test, as though I'm conducting a t-test, number 6. I have to get the standard deviation, and I have to get the mean. So I could put these in my calculator and do the same thing, mean, standard deviation, and set up the test. The main thing to realize here is that whatever number you put here, you put here. We're talking about the mean difference now. And I do put a subscript here for D, but it's the same sort of test. It's still a test of means. And the question is, what number do I put here? Now you obviously have the answer, but I want you to think about what you're doing. You're looking for a difference. The null hypothesis, and this is like the nature of understanding, the nature of the null hypothesis. This is where you have the null, or no difference. Nothing happens, nothing new. So nothing is no better than 0, right? So it's 0. So whatever I put here, I also have to put in the alternative. And depending on if you want it to be an improvement, you use greater than for an improvement. You use less than for a worsening. And not equals for a difference. So depending on the terminology, you could you would pick which one goes in the alternative. In this problem, we want to see, what does it say? We want to conduct a hypothesis test that the yield is significantly greater. So greater means improvement. So that's why I would put a greater than here. So then you follow conducting the test as usual. All right. The best way to review is to study the review exercises. Study the homework and the review exercises, and let me know if you have any questions that I can solve for you. There are tons of videos in this feed that you could go back and look at the end. In December, I did a bunch of exercises with the class, and you can look at those as well. But really, it's just a matter of practice. Before we go, I just want to look at some output together. To interpret output, and then we're going to go. Computer output. So yeah, this is not on the test, right? I just put this here for completeness, or if I have extra time. This is omitted. So there are just a bunch of exercises in here. You should be able to solve them all. Let's just look at this together. Doesn't matter what the question is. Let's look at this output together. This is how computer output may appear. No, the pair testing is on the test, Gerardo. Everything up till here. So here we have mean, a standard deviation, a standard error. You have the confidence limits. You have, so this is a hypothesis test. This is the hypothesis value. This is the estimated value. And then all of this. So what's all this stuff here? So this is from a sample. So this would be the sample mean. This is the sample standard deviation. And this is the standard error, which would be S over N. And you could even check with the N of 4. That's N here. And then these are the limits using the t-test. I know that because, well, I see the t down here. But, I didn't even have to read the question to know that's what this is. So this is the upper limit, this is the lower limit. Now, this is the hypothesis test. So this is the hypothesized value. This is mu0. I know it's for the mean because it says mean. And then this is the sample mean, which is repeated above. Degrees of freedom is n minus 1. And the standard deviation is still S, so don't get thrown off. So that's S. So you can verify what I mean. This is S over N. This is 4.0824829 divided by 4 to prove it. No, not 4. N is 4, yeah. Square root of 4. So that's what you've been given here. And then, depending on which test you want, they give you everything. The software provides you the P, these are the P values. This is the P value for the two-sided test. This is the P value for the right-sided test. And this is the P value if it was a left-sided test. So what I want you to do right now is write out the hypothesis test. Remember, it has to be written like this. And tell me the conclusion. What would mu be equal to? This is output, so we're interpreting output. You don't have to calculate anything, you just have to interpret. You should be able to interpret the results. This is page 61. The hypothesized value is here, 300. And whatever I put there, I also put here. The alternative hypothesis, depending on which one I want, the results are given here. So let's say I pick greater than. So how do you conclude? So you should be able to read output. So you're going to use this result here. You could draw a picture. The t-stat is given to you here. So you could draw a picture for yourself. And this is T3, degrees of freedom. And you will mark the t-stat as 2.44, which is up here, 2.4495, and the p-value gives you 0.0459. That's the information you've been given. So how do you conclude? Right, very good. So then you say, you write p-value less than or equal to alpha means reject. And unless there's any other information, you use 5%. So since our p-value was 0.0459, that's less than 5, so we reject H0. It means whatever. You'd have to go back to see what the question's about, but you see, you don't even have to know the question to know if the test is significant. So there's something interesting here because the test is significant. So this is worthy of publication and reporting. Press release, something is significant. All right, so I am going to leave you and ask that you let me know if you want me to solve any problems online. I can meet with you to solve them, or I can just solve them. Otherwise, you have tons of videos to look at back to December. If you want to know exactly where to look, ask me, send me an email, and I'll give you a date or something, or I'll send a date to the class. But really, if you look in December, by December I'm doing review for the final exam and trying these problems. So work with the review exercises for the final, and the mock exam. That's the best way to study. You should be able to solve the mock exam in 3 hours. The test is up to page 62. It's on the Moodle page. The time for the test is from 9 a.m. We agreed 9 a.m. till 6 p.m. And I described that it would be, the format is already available in, so this is what's happening. This is the format of the test. And this is found, in Moodle. I've put it here, approximate final exam distribution, and you can find the format of the test there. You have the mock exams there, you have review exercises and practice problems. So I did discuss this at the beginning of the class, but some people might have missed it. So this is what you will see on the test. Use your formula sheets to study. Review my videos that I've done for the class, and then go on and review some old videos where I review exercises for the test. And if you need extra material, I think you have more than enough material. Do the homework exercises, and you have lots of stuff to work on. Okay, so if you run out of material, let me know. I'll find some. I'll find more for you. But in terms of, let me see. In terms of the stats review, that's us talking right now. Let's see if I can go to the live videos. So if you went back to December, I think I must have done some reviews on December 10. Oh, I didn't do a lot of classes last semester. Okay, so let's see. Or something's got deleted? Is it possible? I know I did a lot of exercises in June. So if you go to the end of the semesters, anyway, I'll find some videos if you really need more. But really, just work with the notes, and if there's gaps or misunderstandings, let me know. Let's see what I'm doing on December 10th. I'm talking about the test. Do I do any exercises? I did a review of the formula sheet. No, maybe that's not so great. Anyway, so ask me if you want to see any more instruction, and I'll provide you with videos because I know I have them. think maybe in May I did a lot of videos because I felt really bad for everybody. Or April last year. Yeah, we had an extended semester, right? Look at all these videos I have, May. Right, Gerardo, for the short answer, you have to solve problems on paper and send them to me. That's right. If you study the mock exam and you follow, you're going to be fine. If you have gaps, let me know so we can work on clearing up misunderstandings. Okay? I gotta go talk to my niece. So keep in touch, keep me posted. There's a ton of videos here where I solve problems in May for some reason. I had all these different problems. Yeah, so if you want, I can tell you where to go, which videos have good demonstrations. So you don't waste time. Time is of the essence. Okay. Bye for now. Keep me posted if you need any help. Thank you and keep in touch.